So now we're going to talk about how to build a processor pipeline. That is, how do we cut up our single cycle design into making a pipeline MIPS processor. So how should we divide it up? Well, you've already seen this. So we're going to have 5 stages, shown here. The first stage is going to be IF, or instruction fetch. So in this stage, we're going to go and get the instruction from the memory. The second stage is called ID, or instruction decode. And in this stage, we decode the instruction and we do the register read. So here we're going to read the register and decode the instruction. In the third stage, this is execute. So here we're going to do the ALU operation, which is either executing the operation or used to calculate an address. So this is the EX stage. Fourth stage is memory access, and here we're going to access the memory. And then the fifth stage is write back. So here we're going to take the results from that instruction and we're going to write it back into the register file. So it's important to note that the figures that we use here, they're not to scale in terms of time. So it looks like the IF stage is much longer, but that's just because of the way it's drawn. So here's a question. What is missing from this picture? Well, we're missing the pipeline registers. We need to store the state between these stages somewhere. So we need to store which instruction each stage is doing and what are the results of it. So here we have our picture with the pipeline registers. It's got the same instruction fetch, instruction decode, execute, memory, and write back stages. Now the registers between them are going to hold the information produced between the stages, and then they're going to move it to the next stage on the clock. So let's take a look at this. Here's our clock signal. And so what do we have? Well, our instruction fetch has produced something from before, and that's sitting there waiting at our pipeline register. Same way, instruction decode has produced something before, and that's waiting for us. Execute has produced something that's waiting. Same with memory and write back. So what happens here? The clock comes in, and on the clock, all of these registers take their input and move it to their outputs. And now this data is ready to be used. So now we have the data waiting for each stage, and each stage then processes the new data, and on the next clock it'll get clocked in. So we repeat this over and over again. The data walks through the pipeline, and what's walking through the pipeline are the instructions that we're processing and the data they produced. So what are the performance benefits of pipeline MIPS? So here are the numbers that we saw from the previous example on pipelining instructions. And we saw that for the single cycle design, we had to set the clock for the slowest instruction, which was 800 picoseconds. We saw that for the pipeline design, we had to set the clock for the slowest stage, which was 200 picoseconds. And we saw that the ID, that is the register read, and the write back, this is the RF stages, had to be elongated. So right now we only need 100 picoseconds for decode and register read, but in the pipeline, we have to have all stages be the same, so we have to increase that time. It's also important to note that some instructions don't use some of the stages. So the R format and the branch instructions don't use the memory access. Similarly, the store word and the branch don't use write back to the register file. So we're going to need some control logic to make sure stages do the right thing for the right instructions. So here's a question. If we have code that runs all of the R instructions, what percentage of the MIPS pipeline stages will be used? Well, the answer is 80%. So R format instructions don't access the memory, but they do use the instruction fetch, instruction decode, execution, and the write back stages. So the memory stage won't be used if we have only R format instructions. Another question. If we have code that runs all R instructions, that only R instructions in the code, what will the speed up be for a 5-stage pipeline over a single cycle implementation? And here you can assume pipeline registers have 0 delay. Well, we'll be running 5 times faster. We'll complete 1 R format instruction every cycle, and each cycle is a fifth as long, so we'll run 5 times faster. However, we're only going to be using 80% of the pipeline, but that doesn't make the instructions run any slower. It just means one part of our pipeline isn't being used.